Hi, I'm Melissa Wagner, and I work as Associate Director of Science at the Integrated Remote and In Situ Sensing Lab, IRIS, here at the University of Colorado Boulder. I work with drones, also known as uncrewed aerial systems, to study the atmosphere. My focus is on using these systems for atmospheric research, helping us understand weather patterns, damage, dynamics, and more. I've been flying drones since about 2017. I started to use quadcopters to assess tornado damage during my PhD. From there, I went on to create the UAS Damage Science Program at the National Severe Storm Laboratory in Norman, Oklahoma. We used two types of drones. We used a multi-rotocopter and a fixed-wing UAS. The goal was to map tornado damage, especially looking at damage to vegetation and areas impacted by high winds. Using these drones, we could study the damage patterns very closely. By combining that with radar and other in situ observational data, we better understand tornado dynamics and the forces or mechanisms that produce damage. And to dig even deeper, we would also combine this information with high resolution modeling to simulate vortex dynamics. I came to CU Boulder and Iris in 2025 because opportunities opened up for me to continue my research here, as well as expand into other areas of research using other UAS platforms and really a broader range of research that included looking at different processes in the lower boundary layer. There are two main types of drones that are commonly used in atmospheric research. One is the multi-rotocopter. Think of your typical drone, and fixed wing platforms like small airplanes. The multi rotors take off vertically and typically smaller with flight times that range from 30 to 50 minutes. These are easy to deploy, especially in confined spaces, and require fewer crew members to operate. The trade off here is that they have shorter flight times and require more frequent battery swaps. The fixed wing UAS platforms, on the other hand, have longer flight times, so usually over 90 minutes. These drones can take off horizontally or vertically, and some, like the Raven, use a catapult system to launch. These drones are great for covering large areas, but need more crew to operate, including a pilot, a visual observer, and someone to run the ground control station. At the Mobile Uncrewed Systems for Atmospheric Science, or more commonly referred to as MUSAS, we have four UAS platforms. So we have two multi-rotocopters and two fixed-wing platforms. The Raven, which stands for Robust Autonomous Airborne Vehicle, Endurant and Nimble, is fixed wing drone with a wingspan of 7.7 feet. It can fly up to 2.5 hours depending upon the mission and environmental conditions. It's designed for atmospheric sampling, collecting data such as pressure, temperature, relative humidity, and three-dimensional winds information. The Raven can even fly in winds up to 35 meters per second. Then there's Super Raven, which is basically a bigger, stronger sibling, depending upon how you look at it. It has a wingspan of 13.7 feet and can carry heavier payloads. It can fly in winds up to 30 meters per second and stay airborne for about 75 minutes. We also have a couple of multi-rotor copters. So the first one that we have is Copterson. The Copterson is smaller in size, quick to deploy drone that samples the atmosphere vertically. It has a battery life of around 35 minutes and can handle crosswinds up to 22 meters per second. It's a real workhorse for collecting temperature, relative humidity, pressure data, and two-dimensional wind information. The Helix is a heavier copter weighing about 26 pounds. It has a flight time of up to 25 minutes. It's used for more specialized tasks like carrying additional sensors or payloads. For example, in the past, it's been used to measure surface radiation, albedo, and even capturing multispectral imagery that we use for mapping land surface characteristics. So, why do we care about two-dimensional versus three-dimensional wind measurements? So, when it comes to wind, you can measure it in two ways: two-dimensional horizontal or three-dimensional horizontal plus vertical. The difference is that with 2D, we're only looking at the horizontal components, so wind moving left, right, forward, backwards. While in third dimension, we're also measuring the vertical component, so we're including that up, down. In large scale flows, the vertical component is usually pretty small, so we mainly focus on the horizontal aspects. But when we're looking at smaller scale phenomenon like thunderstorms, turbulence, or dust devils, the vertical wind component can be just as important as the horizontal. That's why 3D measurements are critical for understanding these processes better. At MUSAS, we don't just fly the drones. We've got the whole operation set up to support them and the data collection. So we have two vehicles, Tracker 1 and Tracker 2. These are Ford Explorers that help with flight operations, communications, and tracking the Raven. One of them has a catapult system called a Rapcat, which is used to launch the Raven from the roof. These vehicles allow us to stay connected with the drones while they're in the air, ensuring visual line of sight operations, as well as making certain that everything runs smoothly. We also have something called the MURC, the Mobile UAS Research Collaboratory. It's a sprinter van that has been packed with technology, including communication systems, monitors, and computing infrastructure that support UAS operations in the field. It even has a weather station that can be mounted on a 30-foot mast to gather real-time weather data during missions. And we're looking to add edge computing capabilities to the MURC, which would allow us to do data processing, mission planning, and sharing data out when we're in the field. Looking down the road, whether 5, 10 years, or hopefully sooner, the idea is that we want to be able to develop sensors and different ways of measuring things. I'm particularly interested in trying to measure tornadic winds near the surface and better understand their dynamics, because there is a big gap in our understanding and our instrumentations to be able to sample what's going on in tornadoes near the surface. This is very important because this is where we live. This is what's being impacted. My hope is that we can develop a sensor that we can put on a UAS that will help us measure what the wind speeds are, as well as be able to do kind of a profiling, 3D wind profiling of tornadoes, so that we can really kind of understand what's going on. Radar right now can't see it, other instruments can't see it. And so this would really help fill a gap in our understanding of complex tornadic wind flows. I am a geographer, and something that has been kind of ingrained in my education from Arizona State University is that we're very transdisciplinary. So while I'm currently working on certain veins, in atmospheric research, um, there are many other opportunities out there, and working with different partners, whether it's, computer science or branching out with folks to try to understand land cover change. Really, I would have to say sky's the limit on some of the research that we can do, and UAS is one way that we can facilitate that.